Olá! A IUPAP, International Union for Pure and Applied Physics, está interessada em muitas coisas. Dentre elas, a definição das unidades básicas que nós usamos no dia a dia, a manutenção das constantes fundamentais, mas também está muito interessada nos desafios que a ciência tem atualmente. Na área da física são muitos os desafios. Nós temos desafios desde o entendimento das partículas elementares, da matéria condensada, na física nuclear, na biofísica, na astrofísica. Em todas as áreas, ou sub-áreas da física, nós temos desafios. Para que você saiba quais são esses desafios, a IUPAP organizou um workshop especial, que chama-se Entendendo os Desafios da Física Moderna. Cada área da física está aqui sendo apresentada por um líder, membro da IUPAP, e que você terá então agora a chance de entender, através desta apresentação, os desafios que a área apresenta e como os físicos, de um modo geral, estão superando esses desafios para que a física seja um instrumento de entendimento das ciências naturais e que auxilie o homem não apenas a avançar o seu conhecimento, mas a tornar a ciência um instrumento útil da melhoria de vida de cada um existente nesse planeta e nesse universo. Assista e também faça parte do entendimento dos desafios da física moderna. Boa sorte!
So the next speaker is Robert Tribble, speaking on the frontiers of nuclear physics.
Thank you. Today what I want to do is to give a very brief overview of the grand challenges that we face in nuclear physics, and again, very briefly, try to give you a feeling for the facilities that are existing and those that are being developed to try to address these grand challenges. Most of the material that I have in this presentation actually has come from the efforts of Working Group 9 over the last roughly 2 to 3 years. So I thought it would be useful just to start with a few brief words about our working group. Working Group 9 was actually established in 2003 at the annual meeting of Commission C12 as an ad hoc committee on international cooperation in nuclear physics. It formally became Working Group 9 at the 2005 general meeting of IUPAP in South Africa. The membership of Working Group 9 includes the chair, the past chair and secretary of the group, the C12 chair, chairs and past chairs of the Nuclear Science Advisory Committee in the United States, the Nuclear Physics European Collaboration Committee, the Asian Nuclear Physics Association, the Association of Latin American Nuclear Physics and Applications, and directors of major nuclear physics labs around the world. If you look on the website for Working Group 9, you'll find the mandate listed there as a number of bullet points. I only wanted to pick out 3 of these for the presentation today. The first one is that Working Group 9 is to maintain a compendium of facilities existing or developing worldwide, including the science issues in nuclear physics for the next decade. Further down, you'll see we also are to explore mechanisms to enhance international collaboration and, closely connected to that, serve as a forum for the discussion of future directions of nuclear science in the broadest sense. To do that last pair of activities, we have developed a nuclear science symposium that we hold every other year, where we invite the leaders in the field to come give updates on the science and the facilities in nuclear physics. And we also invite funding agency representatives from around the world who deal with nuclear physics projects to join us at that meeting so that they can get updates on the activities, and they can also have time to sit by themselves in an in-camera session to discuss what's happening in their region and also to see how to cooperate on large projects. In our most recent facilities report, we list 5 overarching questions that govern the program in nuclear physics. First of those is, can the structure and interactions of hadrons be understood in terms of QCD? Then, what is the structure of nuclear matter? What are the phases of nuclear matter? What is the role of nuclei in shaping the evolution of the universe? And finally, what physics is there beyond the standard model? What I want to do for the rest of this presentation is to go through these questions one by one and give you a little bit more detail with each one of them, but also tell you a bit about the tools that we have to have in order to attack the problems. So let's start with, can the structure and interactions of hadrons be understood in terms of QCD? So we all know that some number of years ago, now over 5 decades ago, we learned that the proton, the neutron, and other hadrons are not fundamental particles, they're composites. They're made up of a substructure of quarks and gluons. In the 1970s, we got the theoretical framework, quantum chromodynamics, to try to understand the interactions between quarks and gluons. But we've already heard today that that is a very difficult theory to solve, especially in the confinement region. Hence, we've had a number of activities by experimenters over the last several decades trying to provide information that will help guide the theory to be able to do a better job in unraveling what QCD tells us should be going on inside the nucleon. Because we're looking inside the particle, inside the proton, inside the neutron, it takes high-energy facilities to carry out this science. We have 3 such facilities around the world. The first one I'll point out is JPARC, the Japan Proton Accelerator Research Complex, which is just north of Tokyo. This facility has a characteristic that's very typical of these large high-energy facilities. It's got several stages of acceleration, starting with a relatively low-energy beam here into a synchrotron, which increases the energy, which then puts it into a final synchrotron to give it the final proton beam energy, which is today running at around 30 giga-electron volts and a output power of about 750 kilowatts. Using the earlier stages, JPARC actually produces neutron beams for use in condensed matter physics. But for nuclear physics, the primary beam that's used comes out of the what they call their 50 GeV proton synchrotron and heads into an area here for the hadron hall, where you can produce secondary particles that you can then use to study the interactions of hadrons and get some ideas about what's happening in the QCD construction of those hadrons. Also at this facility, a neutrino beam is produced by dumping the proton synchrotron beam into a beam dump and sent off to Super Kamiokande. And that's used to study neutrino properties, which is another purview in part of nuclear physics, as I'll point out later. In the United States, the primary facility devoted to the structure of hadronic physics is Jefferson Lab. Jefferson Lab has just recently completed an upgrade to double its beam energy from 6 GeV electron beam up to 12 GeV. And they've then also improved some of the apparatus in the end stations available at JLab. This electron beam on nuclei allows us to look primarily at the quark-like degrees of freedom inside the nucleus. In Europe, the primary facility for this research is at the moment called GSI in Germany. It's transitioning into a much bigger facility called FAIR, with all of these parts being new construction that's now underway at GSI. The primary facility at FAIR that will be involved in hadron structure is the antiproton storage ring, which will allow us to have a fairly high concentration of antiprotons that can be used in scattering experiments to do effectively particle-antiparticle type interaction studies. Down the road in the future, the United States is looking at the prospect of building an electron-ion collider where we would have a high-energy electron beam that could interact with a high-energy particle beam. This is about the only way that we've been able to come up with to date to really get at the question of what's going on with the gluons inside the nucleon. This is a very, very complex problem, and in fact reminds me to mention that over 90% of the mass of the nucleon comes from the gluon field. It's a dynamically produced thing, and we don't understand it at all these days. There are two different versions of an electron-ion collider that are being considered, one at Brookhaven National Lab and one at Jefferson Lab, and they would have similar characteristics but would be produced by doing different construction projects. There's been a lot of work on the reasons why an electron-ion collider should be built. And there's also today a National Academy study going on in the United States to look at the science case for this, which would probably be a roughly $1 billion investment in a new science probe. So let me turn to the second question. What's the structure of nuclear matter? This is perhaps a rather familiar chart to many people, a chart of the nuclides. The stable nuclides are shown as the black squares, and the unstable beta unstable nuclei that have been measured are shown in this roughly yellowish color. What you see in the green shade outside is what we expect to be the line of particle stability on both the proton and neutron-rich side. We expect this, but we have no clue as to how accurate our expectation is because we are very far away from being able to probe, especially on the neutron-rich side, this line where we think stability would cease to exist. We're making a lot of progress on understanding nuclear structure now, and that's being done by primarily advances in effective field theories. Back in the 1980s, we could do ab initio calculations and understand the helium nuclei. Now we're able to understand through similar ab initio calculations nuclei up beyond mass 50, and we should be beyond mass 100 in the very near future. And that's because of advances both on the theory side and advances in computing. But we are still quite a ways away from having a really comprehensive predictive theory of complex nuclei. That's been a key goal of the field for many decades. It still remains a key goal of the field. What we have learned in the last couple of decades is that in order to really understand nuclei, even stable nuclei, it's important to measure properties of nuclei fairly far from stability. We get different degrees of freedom that come into play when we do that. And because of that, we have actually had a major effort in developing high-power facilities, radioactive ion beam facilities around the world. This map shows you a compilation of the various regional facilities that are now either existing as radioactive ion beam facilities or under construction or in a design and R&D stage. And you can see that there are a fair number of them around the world. And the investment that has been made over the last roughly decade or so is on the order of about $5 billion in developing these new facilities. With these, we'll be able to probe much further off the valley of stability to look at nuclei that we haven't been able to observe today. So let me turn then to what are the phases of nuclear matter, the next question in our list. Starting with fixed target experiments at CERN and Brookhaven, people began investigating the properties of of the nuclei that you could produce using a very high energy heavy ion beam, initially on a fixed target. What we learned was that we were producing a new state of matter by those reactions, and that new state of matter we were able to really quantify in detail when the relativistic heavy ion complex at Brookhaven National Lab came in, online around 2000. We had quite a shock when we fully unraveled what was going on inside the collisions that took place at RIC. And that was, instead of having a material that looked like a gas, we were producing a quark-gluon plasma type material that had very fluid properties. In fact, what we can measure today is an entropy density in the QGP that puts it as close to the quantum limit as any fluid that has been observed in nature. This surprise has been upheld by work that's been done now at the LHC at even higher energies than we have available at RIC. The primary detector at the LHC that's been involved in this work is the one that's been put together by the ALICE collaboration. And this shows all the particles coming out of a lead-lead collision at about root S of 5 TeV. From the work that's been done over the last roughly 20 years now, we have a pretty good view of what the phase diagram looks like for the material that's produced in these heavy ion collisions. This phase diagram has properties that are actually quite similar to other phase diagrams of matter. In fact, if you look at this, it looks a bit like the phase diagram for a high temperature superconducting material. What we have in the case of our QCD phase diagram, though, is a plot for the baryon chemical potential versus temperature. And you can see a line here. This is the part of the phase diagram that the Large Hadron Collider can explore with its heavy ion collisions. The region in here is the part of the phase diagram the relativistic heavy ion collider can explore. And we expect somewhere in here that there was likely a critical point. We don't know where that critical point is. We don't know the nature of that critical point. And in fact, that's one of the major issues that we would like to try to understand over the next few years. That we can do by doing a beam energy scan that allows us to go through this region at the relativistic heavy ion collider. And that beam energy scan will be done by one of the two detectors at the RIC, the STAR collaboration detector. We turn now to the next question. What's the role of nuclei in shaping the evolution of the universe? This is our sort of classical picture of the Big Bang. And we know that roughly microseconds after the Big Bang, we go through a quark-gluon plasma phase in the early universe, out of which comes the protons and neutrons that make up the first particles. Within the first few minutes of the Big Bang, we have enough energy and density in the particles that are produced to have Big Bang nucleosynthesis take place. And that gives us a universe after the early stages that has mostly protons, a little bit of helium, and a little bit of lithium. It takes some long period of time, actually, for this material to coalesce into the first stars. After that coalescence takes place, nucleosynthesis begins to take over. And in fact, we know that there are now many processes that occur in stellar evolution in the nuclear synthesis world. Of course, we have the standard hydrogen and helium burning that takes place in stars like our own sun. But in addition, we have a lot of other processes that take place in explosive environments, such as in supernova, in X-ray bursts from neutron star paired with a giant star typically. We have processes that take place in neutron star mergers, many different areas where we can have nucleosynthesis. What's shown here are a couple of the important processes, the rapid proton capture process, which takes place in an explosive environment like an X-ray burst, where protons are captured very rapidly along the line of proton stability to produce nuclei up to sort of the strontium region. The flip side of that is a rapid neutron capture process, which again involves very rapid neutron captures and beta decays out all the way to nuclei that can undergo fission. And we know it's this process that leads to these nuclei that we found on Earth, uranium and thorium, that have no other path to get there other than the rapid neutron capture. We also have, of course, slow neutron capture processes that can take place. So just a rather large variety of things that we have to understand. And for example, to understand the role of these processes and the abundances in the light nuclei, there are many reaction rates that we have to get from unstable nuclei, proton captures on unstable nuclei. And that is, that's turned out to be a difficult process to do in many instances now, but we're making headway, and I'll point that out in just a moment. For the heaviest nuclei, to understand their abundances and how they're actually produced, we really need to understand the R process, this rapid neutron capture process, and that means we need information about nuclei very far from stability on the neutron-rich side. So there are a wide range of tools that we have to use in order to do the nuclear astrophysics studies. We're using the radioactive ion beam facilities to produce secondary radioactive beams that we can use then to study proton capture reactions on unstable nuclei. But we also need high-intensity light ion beams at very low energy to understand in detail some of the other less exotic processes that take place in stellar evolution. We also are now finding more and more use of accelerators in underground laboratories to measure cross-sections where the background has to be extremely low. And of course, all of this is put together by extensive modeling calculations and network calculations in order to actually move from the measurements we make in the lab to a predictive theory for stellar evolution. So let me turn to the final question in my list. What physics is there beyond the standard model? The standard model has been enormously successful in predicting physics properties for the last 5+ decades. We don't think it should be that successful because there are reasons why it should fail. And I've just listed a few of those in here that are often quoted as reasons for it to not be the final answer. So it's been the purview of both nuclear and particle or high energy physics to search for breakdowns of the standard model for many, many decades. In nuclear physics, the efforts that we are carrying out involve a wide range of activities at a wide range of facilities. In low energy processes, we can look for deviations from standard model predictions in nuclear beta decay and muon decay. We also have groups that are doing searches for the electric dipole moment, both in the neutron and in nuclei. This would be a determination of time reversal violation if we can find such a electric dipole moment, which could give us some hint on what's happening with the matter-antimatter asymmetry in the universe. We also have precision measurements underway of the anomalous moment of the muon. This is one area where we seem to have a hint of a possible breakdown of the standard model, but today it's only about a 3 sigma deviation, which is not enough to say for sure that it's a breakdown. In addition, we have measurements of parity-violating electron scattering, very high precision measurements of this process that allows us to look at the running of the weak coupling constant sin squared theta W. And primarily at CERN, but soon also at FAIR, we have symmetry measurements in antimatter, which can allow us to test the matter-antimatter duality. There are a number of other efforts where nuclear physics and high-energy physics overlap significantly, and that's in areas such as the search for neutrinoless double beta decay and determining neutrino properties, neutrino masses, the mass hierarchy, the mass mixing and CP violation are all areas of great interest, and that's one of the activities that the neutrino panel, which I think will come up for discussion again tomorrow, will look at. And we have efforts mostly now being carried out at the facility at J-Park looking for decays of the K-meson that are not allowed again by the standard model as ways to test for the breakdown of the standard model. And finally, I'll just point out that a number of groups are looking for dark matter. We don't yet know what dark matter is. We have many ways that we are looking for it. So far, none of them have succeeded. So let me wrap up by just commenting that we have a wide range of problems being attacked in the field of nuclear physics in order to understand the interactions ultimately that govern the evolution of the universe. We have multi-billion-dollar investments being made around the world in new capabilities in order to allow us to attack these problems. And finally, I want to point out, I didn't have time to talk about it in any detail here, but the field continues to have many applications, for example, in areas such as medicine, accelerators for industrial applications, and power. So with that, I will finish up.
Thank you very much for this beautiful talk. Questions? Yes, over there. Oh, you only have 2 microphones. Okay, so I will go myself.
You can have my microphone.
Thank you for the overview of what's happening in nuclear physics. I just have one question, though, that I need clarity on. In this heavy ion collisions experiment, is it concluded that quark-gluon plasma has been produced? Thank you.
The evidence for the quark-gluon plasma is very strong these days. Many different ways to look at that. What we find when we look at the collisions of 2 heavy ions at the energies available at the relativistic heavy ion collider is that the remnant that's left, the material that's produced in that high energy density environment, decays in such a way we get the same number of particles and antiparticles out of it. It's very clearly an equilibrated system that is not from the primary ion. It's a remnant material that's been heated up to very high temperatures and that has melted basically the constituents that were used to produce it.
Further questions? Okay, back there.
So I have a comment and a question. The comment is just to add atomic physics to, and perhaps Bill was going to say the same thing, to precision measurement. In atomic physics, set constraints on nuclear physics, such as searches for electric dipole moment and dark matter and many other examples. And so my plug for atomic physics. The other question actually is, what is the status of the flare facility at GSI, which would be needed for anti-hydrogen studies?
So FAIR is now under construction. They had groundbreaking ceremonies in the summer. They are forging ahead. I will be there in about 3 weeks. If I had been there before this meeting, I could give you a better update. But as of this summer, they're moving ahead with construction. Civil construction is underway now. They actually have most of the magnets they need for the synchrotron in-house. They were there last year even. So it's moving forward at this stage. I'm guessing about 4 to 5 years before they'll have the first beams out from the new facility.
So I'm wondering about the issue of exploring the phases of nuclear matter, like the quark gluon plasma and these heavy ion colliders, with respect to the question of, is the system large enough to essentially be in the thermodynamic limit that allows you to talk about the kind of phases that you would calculate for that kind of a system? I mean, with a 3D system, even with pretty heavy ions, it's not that big. So what's the deal?
So yes, that's a question that was attacked very early on. There are many ways that one can look at the equilibration of the system. The flow properties of it give us a lot of information about that, and all of the data that we've obtained are fit extremely well by hydrodynamic calculations based upon thermodynamic equilibrium. They're not described by any other model at the moment. So that's what we have to hang our hat on.
Well, my question is not so much whether you're in equilibrium, or whether you're just big enough.
So the size of the system to me is not as important as the time scale. This is a system that lives very, very short time. And so that equilibration takes place extremely rapidly. I mean, we're talking about 10 to the minus 22 seconds for the time for the system to be as a plasma. The size of it is, again, going to be not macroscopic by any means, but there are a huge number of particles that come out from this interaction region. We got at Rick up to sort of 4,000 to 5,000 particles coming from a single collision. At the LHC, it's much higher than that.
I have one question. Could you comment on the search for super heavy element, which, as you know, what are the prospects for discovery, which, as you know, is a matter which is of great interest for IUPAP?
So another area of interest that I didn't have time to talk about at all in the presentation here, super heavies are probably going to be some years away yet from discovery, because what we are learning is that we can get into the Z region, but we can't get into the Z and N region where we would expect stability. And so that requires a whole new approach to the problem. Much of the work that's been done over the last roughly 15 years has involved using very neutron-rich particle beams, typically at fairly low energies, to fuse together systems to produce very high Z material. That doesn't give us enough neutrons to stabilize that material, and we don't yet have a mechanism to get there. So it's a work in progress, a lot of effort going on, in particular at Dubna, to try to come up with new ideas and new techniques to get us there, but it's not going to happen soon.
Okay, in view of the time, I think we should move on. Thank you very much again for the talk.